Okay. Now I have to do two more kinds of learning. One is learning the structure. Okay. Up until now we have been saying the domain designer gives us the structure and we use this structure and estimate the probabilities using data. But the domain designer could say, I do not know the structure, or I only know approximately the structure, why do not you use the data to figure out the structure also. That is called structure learning. There are a lot of papers that were written in structure learning in the 2000s, but it never became very successful. But I will give you the general idea, and the general idea is, because structure is a discrete subject, let us do search over the structure space. So, how do you do search over the structure space? So, I give you a structure, based on that structure you learn the parameters, based on those parameters you see how well it fits the data, and then you go back and make some local changes in the structure, right. And what do you mean by making changes in the structure? Suppose I give you one structure, how can you make changes in the structure? What operations could I do? Delete or add an edge, very good. So, suppose I give you this middle structure like B E goes to A goes to C, then I can define some operations that will change the structure. One operation could be add an edge, like I add an edge from E to C. One operation could be reverse an edge, like I reverse the edge from E to A. One operation could be delete an edge, like I completely remove the edge from E to A. For each set of structure I can learn probability parameters by maximum likelihood or MAP or whatever. Then I can compute some score of what is the probability of generating the data and so on. And now I can keep doing this using local search. Can somebody see a problem in this? It is hard to see, but if you can see, that will be awesome. Can somebody see a problem in this approach? Vishwajit, you have to be louder. Very good. So, Vishwajit says, I could keep on adding edges. By continuously adding edges, am I increasing my parameters or reducing my parameters? Increasing my parameters. If I have more parameters, then will my optimization usually lead to a better fit or worse fit? See, I have more degrees of freedom. So, it will typically lead to a better fit. So, what would I do? I will add an edge, my fit will increase. Then I add another edge, my fit will increase further. I keep adding edges, eventually I will have a highly connected Bayesian network with a humongous amounts of parameters, and I have what is called overfit on the training data, but it will not generalize very well. So, in order to fix this, I use what is called the Occam's razor or the KISS principle. Do you know the KISS principle? Okay. So, the KISS principle is keep it simple. What we are saying in the KISS principle, or it is also called the Occam's razor in the language of machine learning. Occam's razor states that a more complicated model must pay a heavy penalty for being complicated. So, the degree of fit should become so much better that you are allowed to add another edge, and we accomplish this by adding a score which is for model complexity. So, maybe number of edges, exponential of number of edges or something like that, you add to your degree of fit. So, now they trade off, they fight with each other. If adding an edge increases the probability, it reduces the score for model complexity, but if it really increases the fit much more, then it reduces, then it is you should add this edge, otherwise you should not add this edge. And how do you trade these off? So, all of that you will learn in machine learning course. So, this is one way of what is called regularization of the model. This is a technical term which says that I want the model to be less complex, more regularized. Okay. Now, the last algorithm. I am going over this a little fast, I am sure you can see this, but these are important nuggets of insight, and these are the first time we are introducing these concepts, we do not have to go into the depth for now. Okay, so, the last algorithm, and one of my favorite ones in this class. So, let us say I do not give you full data, Let us say I tell you that the data is 0 1 1 1 0 0 1 1 1, and then for the fourth data point I forgot to check the value of B. Now, this would often happen in the real world. Now, you are trying to learn a Bayesian network, you send somebody into village, you ask people, okay, go and check the vital statistics of every newborn in the village, you check their height, weight, gender, etc., and you forgot to check their temperature or whatever. The thermometer was broken that day. You wrote down the temperature, but there was rain and the raindrop removed the temperature. All of these things happen in the real world. In the real world, data is highly noisy, which we are not going to talk about, but data is also often incomplete. What do I do when I have to learn from this kind of data? Now, this is what I describe as a chicken and egg problem. Why is this a chicken and egg problem? Because if we had the chicken, we would have eggs, and if we had the eggs, we can get chicken. But the problem is we neither have chicken nor the egg. In other words, if we knew the missing value, if I knew the value that is question mark, can I do learning? That is what we have been doing this whole class, maximum likelihood, MAP, whatever your favorite, let us say ML, you can do learning. However, if I knew the parameters of this model, if I knew probability of A, probability of B given A, probability of C given B, if I knew the parameters of this model and then I was asked to compute the missing value, it is called imputing the missing value. If I was asked to impute the missing value, I would have to ask the query, tell me the probability of B given A is true, C is false, and the model will use its probability distribution to give me some inference probability. So, if I knew the model, I can do inference to figure out the question mark. If I knew the question mark, I can use learning to figure out the model. The problem is I know neither of the two. Now, this would happen a lot in your life, I am telling you, I have seen this, felt it. You will always have two sets of problems, one problem determines the second problem determines the first, you do not know the answer of either of the two. In all such situations, do what is obvious. What is obvious? What is obvious? Assume some initial value, let us say of the parameters, then you use those parameters to compute the missing value, use the missing value to compute the parameters, use the parameters to compute the missing value, you keep going back and forth, mutual recursion, and that is it. What is your name? Roshan. I am telling you, often the obvious thing is the right thing to do and a hard thing to prove anything about. But in the case of this Bayesian network setting, this algorithm is called the EM algorithm, and you can prove many interesting theorems about it. You can also prove that it converges, and under certain conditions the estimates are really good. And the reason it is called the EM algorithm is because when we are doing estimation, when we are computing the question mark, that is called the expectation step, because we are doing inference, we are doing the expectation of B given A comma C. And then when we are using its value to estimate probabilities, then we are doing some maximization, because argmax of theta, and so that is called the maximization step. And this, now the slides show you the example. Let us quickly run over the slides. So, let us say I initialize the values like this, and then in the E step I estimated what is the probability of the question mark equal to 1. I use Bayes rule, and that gives me the probability 0. If that value is 0, so then I impute the missing value to 0. If I impute the missing value to 0 and then re-estimated the probabilities, I will get these probability estimates. Then I reuse these probabilities to re-estimate the probability the question mark is equal to 1. If I get the same value, I have converged and I stop. Now, of course, this example was written so that it can fit in a slide. In practice, you do not do it like this. First of all, you do not start with probability 0, we do not like zeros, right. Secondly, when you do the E step, you will not get a value between exactly 0 or 1, you will get a value close somewhere in the middle, let us say you get a 0.8. Then you do sampling. So, either you sample and you say 0.8 means I will say this value was 1, or you say that 0.8 means that I will make 0.8 of a data point which has value 1 and 0.2th of a data point which has value 0. And this is what is called soft EM. The first case was called hard EM. So, pretty much everybody uses soft EM in practice because that converges better, and then your convergence condition is that your probability estimates do not move by much. This algorithm is a very important algorithm and has a lot of really nice properties, as I said. Okay. So, this is called expectation maximization. You guess the probabilities of nodes with missing values, you use those to compute the probability distribution over the missing values, then you update the probabilities and then you repeat until convergence, and this is guaranteed to converge to a local optimum. So, this is the summary of what we learned today. If I know the structure and every data point is observed, we just need to do parameter estimation, we can do ML or MAP or whatnot. If I do not give you the structure, but I give you full data, then you can do structure learning. For example, you can do local search through the structure space. If I give you known structure, but missing values, you can do expectation maximization. If I give you unknown structure and missing values, you will have to first estimate structure, then estimate, do EM, then re-estimate structure, then do EM, that is called structural EM. And then there are even harder problems that I am not going to talk about. The last thing I want to say, because we are now coming to the close of this whole big series on Bayesian networks, is that Bayesian network is one of the many models. It is the first model that we learn, it has a lot of intuitive properties, it is a directed model, but then there are also undirected models. When it is hard to figure out who is going to be the parent, we often use undirected models. An example of an undirected model is a Markov network. And in fact, Bayesian network and Markov network make some similar conditional independence assumptions, and in fact, you can convert a Bayesian network into Markov network by just marrying all the parents, and that process is called moralization. So, if you start with the first Bayesian network and then you marry all the parents, like for example, parents of B are X and C, you marry them and add an edge and remove the arrows, that creates an equivalent Markov network, and that process is called moralization. There are also models which have both directed and undirected edges, for example, chain graphs. I also want to point out that there is a full theory about the kinds of models people find in different applications. For example, we have learned the most difficult or most general form of Bayesian networks, the directed generative models, but specific structures where let us say I have one set of parents which transition between each other and a set of observations which depend only on the current parent, is what is called a hidden Markov model. Very famous model, so right from the 80s, a lot of machine translation, speech recognition, a lot of NLP applications, everything used to be done using hidden Markov models. The very simplest form of Bayesian network is called the naive Bayes algorithm, where there is one parent and lots of children, and it is a very important algorithm that you will study in your machine learning course. So, after we have discussed what we have discussed, you will find many manifestations of these models, and you will find all them to have much simpler characteristics than what we have studied in our class. And of course, equivalently there are non-generative models like conditional random fields, CRFs. There is a general CRF, the linear chain CRF, and logistic regression, which is the most simple form of CRF. These are heavily used in a lot of machine learning applications, and this is where we will stop talking about this and we will start talking about something else from the next class. So, thank you.